let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another installment of Math 391, Ordinary Differential Equations. Just had a quiz. Hopefully that wasn't too bad. But we shall continue. Good news is that, we used up some of today's class for a quiz, but the good news is today's class is going to be mostly computation. I know the last few classes have been very theoretical, and some of you are like, I get it, I understand. It's important, but I do understand that getting through the theory sometimes can be a little bit of a drudgery. And so today, we're actually going to be doing mostly computation, so nothing really new to learn theoretically. We're pretty much going to spend the rest of the time going through examples where we spoke about last time power series and how to use them to solve differential equations, but we didn't actually get to an example. So pretty much today, we're just going to go through a bunch of examples. That's the plan for today. So let me share the screen here and we can get on with our lives. So this is what we started last time on the 2nd, right? We are in chapter 5. We did a review of power series. And the idea of what a power series is just an infinite polynomial. What it means to when do they converge? They always converge. So there was a problem in the quiz that said, oh, it diverges for all x. Obviously, that would be false because a power series will always converge. It's just a matter of where they converge. Where they converge is called the interval of convergence, and half the length of that interval is called the radius of convergence. Absolute convergence is actually important, and we can derive certain power series for well-known power series for certain functions centered at 0. We call these guys Maclaurin series. And these guys happen to be absolutely convergent. So we're allowed to do calculus with them, and that is very convenient. Pretty much any power series that converges absolutely on some interval, we can actually do calculus with that power series on that interval. We can differentiate it, we can integrate it, we can do all sorts of things. Okay. Now, that being said, we can actually use power series to solve ODEs. And it turns out it's actually a very useful numerical way to solve an ODE. Right. I also spoke about some properties of series that we're going to be using in a little bit. So here was the process to solving an ODE using power series. Now, the nice thing about this is that we know how to solve, for example, soldes. That's what we're going to be using for the rest of the time. What we're doing can apply to higher order ODEs, and it would be very similarly applied to what we're doing. So there's really no need to go beyond the solde. So what we're going to do is we're going to go through these steps for solving an ODE, a linear ODE. Basically, we're going to assume that the series solution has this form. It's a power series centered at x0, where x0 is the point where we're given our initial conditions. Right? So it starts at that initial condition and it fans out, right? So there was a problem in the quiz that asked you, well, if we could find a power series solution, what would its radius of convergence be? Well, first you'd find the interval where you can find the solution. Then you'd find where the center point is. And of course, you only can extend from that center point to the edge of the interval where it was applicable. And I believe for the quiz, the answer was a half, if memory serves. Anyway, so yeah, so let's actually go through this process, go through a few examples and get these guys. So the first step is to assume a solution that looks like this. We're going to find all its derivatives and we're going to plug it into the ODE. And essentially we're going to shift things around. We're going to simplify, basically want to get to a point where we can combine all series. Once we can do that, we can equate the coefficients of the series on both sides of the equation. This gives us something that's called a recursion formula, recursive definition. They're called various things, various combinations of these words right here. And that allows us to actually solve for the A's, in which case we can write out our solution as a series. Every now and then we see that our series is something nice. It actually converges some that we know about, but sometimes it's not nice. And it turns out that the series is still good enough because we can just approximate the solution using a finite number of terms or a finite polynomial, and it would work reasonably well within some degree of accuracy or within some interval that we care about. And so that's pretty much it. And you guys try this. If you got through them, great. If you didn't get through any of them, that's fine, because we're going to go through them now. So we're just going to go through the process here. You guys have the PDF of the process and all that good stuff. So I don't really need to explain anything more, really. It's just going to jump into computations. So let's actually do this. Started here on 7.7. And we're coming down to the end of the wire, guys. We have how much? So our final is on the 23rd. So our final is 2 weeks from Thursday coming. So you guys need to, we're gonna start wrapping this thing up. Let's get with series. Yeah, time flies. I was looking at that earlier today. I was like, what? File's like 2 weeks from now. It's gonna be interesting. Okay. All right, so here is a differential equation, linear, constant coefficients, not a big deal. We actually know how to solve this guy already. If you found the characteristic equation for this guy, I'm just spitballing here, we'd get r squared plus 1 equals 0. The solution, the roots of that equation are plus or minus I. So we know that it would be C1 sine of t plus C2 cosine of t, or vice versa, it doesn't matter. So that we actually know what the solution is to this. So let's see what a power series solution would actually look like. So here's how we do it. So here, now, I'm gonna write these guys in green because you don't have to write this all the time. Or maybe I'll just write down the first one. Assume y is equal to the series of an x minus x naught to the n, i.e., it's the series of an x to the n, because our x naught is 0. Plug in 0 there, I'm only left with x. Now it is a regular old power series, so we're assuming that this starts from 0 and goes off to infinity. Now what we would do is we would find the derivatives. So basically, we can differentiate term by term. This means that your y prime is going to be n x to the n minus 1. Just differentiate n x to the n, get n x to the n minus 1. Now you're allowed to bump up the index here. Now this little step here is optional. You can leave it or you can do it if you want. And the idea is, if we start at n equals 0, if we start at n equals 0, we add 0, so it makes no difference. So we can just start from 1 to get all the non-zero terms. But other than that, as well as below that, our y double prime is going to look like n times n minus 1 times an x to the n minus 2. And again, I can bump this up, because if my n is 0, I'll get 0 because of the n factor. My n is 1, I get 0 because of the n minus 1 factor. And so my non-zero terms start from 2. Again, optional. You can bump this up, but it's nicer. A lot of times it's nice. And you can realize that if for any reason you need to go back to n equals 0 at any point, you can do so at will and not have to worry about it. So that's your y double prime. Now, in general, you don't need to write this down. It's something that you would just know what these forms are. You don't need to write this down. So once you assume your y looks like some sort of power series, differentiating that power series should be no problem. You can do it on the fly. You don't need to do an extra pair of lines to actually write it down saying that, oh, I'm doing the derivatives and this is what they are. Now what you want to do is you want to actually plug into the ODE. Okay, so I'm going to go back to the original y double prime plus y. Where I see y double prime, I'm going to plug in its series. Wherever I see a y prime, I'm going to plug in this series. Whenever I see a y, I'm going to plug in that series. So I'm going to go in, and it's just y double prime plus y. So this here is the series n equals 0 to infinity, n times n minus 1, a n, x to the n minus 2, plus series, n goes from 0 to infinity, of a n x to the n. This is equal to 0, which, by the way, I can think of this as the series of 0 x to the n. That's going to be important for later when I want to match up coefficients, right? I can just think of it as an infinite sum of zeros. Okay. So now the idea is you want to combine all the series. So if you have several series on the right and on the left, you want to combine all the guys on the left, you want to combine all the guys on the right, and then you want to match up the coefficients together to find what the A's have to be. Now, in general, to match up this series, you want them to either, I already said we were going to bump this up and start at 2. You need the series to have the same powers. So what you do first is you fix the powers, because you want to have a common term where it can like factor out the x to the n. Make them n as in the assumption. Pretty much you're going to want your powers to look like whatever you had in your assumption. So in our assumption, we assumed our y looks like a n x to the n being the variable term here, which means if I have x to the n minus 2, that's already going away from what my proposed solution was. So the first thing you want to do is you want to actually bring it back to that. So we can do here is we can shift. So last time we spoke about shifting, this was Thursday. Let me quickly remind you what that is. At any given time, I can shift all my n's by adding a constant or subtracting a constant, and just literally replace all the n's with that shifted form. And the series will actually output all the same values, right? So that's what I'm going to do here. I'm simply going to shift. So for this one, I'm going to shift all n's and shift them over to be n plus 2's. Once I shift all n's to n plus 2's, that will turn this n minus 2 in the power to an n, right? Now what's going to happen here is that the series will now start at, well, let me actually do that and write it out so you'll see what's happening here. So this first series is going to become the series and everywhere I see an n, I'm going to put an n plus 2, n plus 2, n plus 2, n plus 2, n plus 2. Literally everywhere I see an n, I replace it with an n plus 2. And so that's going to lead me to the next line. Now notice here where the n plus 2's, that's now going to, I subtract 2 from both sides, and it's going to go back to a 0. So that's nice, right? So which is why sometimes it's nice to actually shift it with the derivative, because then once you shift the powers, you end up shifting it back to a 0 and you get something nice. If I left this at 0, then I'll start out with here being n equals 2, and that will have, might have some issues that I don't want to actually deal with. So now our first term looks like that. The second term was already fine, so I leave that. And we have that. And seems everyone's with me so far, so let me keep going. No one's complaining in the chat that they don't know what's going on, so that's good. The next thing you want to do is get the indexes to be the same, or indices is the proper plural. The indices are the guys that are right here, like the n equals zeros, right? These are already the same, so let's move on. We'll see examples where they're not the same, and you'll see how you have to do it. So the next thing you want to do is combine the series. Now, once the series, the x term is the same, and they start at the same point, I can now apply one of those properties I gave you guys before, namely this guy, and I can write the sum of two separate series as one big series by just combining the like terms. So now I would have there's one big x to the n out here that I can actually combine. Now, the series starts from 0 to infinity. And in the first term, I have this as the coefficient. So this is n plus 2, n plus 1, a n plus 2. There's an x to the n, but it's common. I already factored it out. Then in the second term, plus I have an a n from the term right here. So that's what we have. Now what we're going to do is, again, remember, this side I can think of as that power series. So now what I can do is I can match these guys up. The 0 here must be equal to the 0 here. So that leads us to the next situation. Equate coefficients. This means that your n plus 2 times n plus 1, a n plus 2 plus a n must be equal to 0. This guy is called the recursion formula. Or recursion relation. Or instead of recursion, you might call it recursive. So they can call it the recursion formula, or the recursion relation, or the recursive formula, or the recursive relation, but that's going to be the guy. Now, once you get here, you solve for the term. With the largest index. Now in this situation, the an plus 2 is going to be the guy with the largest index. So I'm later going to solve for an plus 2. Bring over the an, and then divide by n plus 1, n plus 2. Now, this is the guy that I like to call the recursion formula. I usually bring it to this point, but sometimes if they don't solve for the largest index, you can call it. So this is what I like to call the recursion formula. But it's of course exactly the same equation, but I'd rather you think of this as the recursion formula. Now, what does that actually do? This helps us find the a's. And that's actually going to help us solve the problem. So let's actually see what this is going to look like. So remember, your a0 is going to be your y of 0, which is given or leave as a0. your A1 is going to be your y prime of 0, which is given, or leave as A1. Right? Essentially what you're going to realize is when these guys aren't given, they're essentially going to form the C1 and C2 that you usually remember from the homogeneous solution. And so now, for A2 and beyond, use the recursion formula. So for A2, you realize what I can do. To find A2, I can go to this formula here, and I can plug in n equals 0. That will give me A2 on the right side. So if I plug in here, n equals 0, I would get A2 on the left side. Over here, I would have minus A0 divided by 1 times 2. So my A2 is that. Now you literally go through and you find as many terms as is required, or as many terms as you would need to see some sort of pattern, or as many terms as you would need to approximate the solution to within some degree of accuracy. Now, in that last case that I just mentioned, you'll never have to worry about that in this class. However, there are going to be times where we're going to specifically ask you how many terms. Find the first 4 non-zero terms or something like that, for example. Otherwise, we might just say, find what the closed form of the answer is, and then you have to really think about patterns. So what I'm going to do is I'm actually going to find more terms than is probably usual here, just because I'm hoping there is going to be a pattern. So for A3, I would plug in n equals 1 here. That gives me minus A1, and here I have 2 times 3. A4, I can get A4 by plugging in n equals 2. If I go up here and plug in n equals 2, I would get minus A2 over 3 times 4. Now, I would actually rewrite that. You see, my A2 was minus A0 over 2, so this becomes A0 over 2 times 3 times 4. And this is an important point here. We want all AI in terms of, and you're going to see why soon. So my A2, I could write it in terms of A0 or A0. My A3, I could write it in terms of A1. My A4 came in terms of A2, but I rewrote that based on what I knew A2 was to get A0. So this is a recursive formula. As you would remember from recursion, is you use previously known terms to figure out new terms. And so that's what we're going to do. So we're going to keep doing that. So here for A5, and maybe I'll just do 2 more here. It'll be enough for you to see the pattern. For that, I'll need to plug in n equals 3. Now, if I go here and plug in n equals 3, I get A3 over 4 times 5. Get minus A3 over 4 times 5. Now, of course, that's in terms of A3, no bueno. I can write A3 in terms of A1, so I can replace that. This will become positive A1 over 2 times 3 times 4 times 5. One more, and I'm not simplifying those for a reason. If I do n equals 4, that would give me A6. I go up here, plug in 4. I don't like how that A6 is. So go up here, plug in n equals 4. That gives me a6 on the left. On here, it gives me minus a4 over 5 times 6. Don't want that in terms of a4. So then I'm going to replace this a4 with up here. A4 was actually a0 to divide by 2 times 3 times 4. So this becomes a0 divided by 2 times 3 times 4 times 5 times 6. And hopefully you're already seeing a pattern here. Right? So hopefully you're seeing that there's a pattern in the denominators that are factorials. This I can think of a minus a0 over 2 factorial. This I can think of as minus a1 over 3 factorial. This guy here I can think of as a0 over 4 factorial. This guy here is a1 over 5 factorial. This guy here is a0 over 6 factorial, and so on. So now what we can do is we can go back and we can start to find our solution. So remember what we assumed our solution looks like. We assumed our y is equal to the series of a n x to the n, right? That was the assumption that we made in the beginning. All the way up here. I'm explaining a lot. This problem shouldn't be that long, but I'm just explaining everything I'm doing, so it's taking a while and a long time to write down. That was our assumption, which means we can actually write this guy out. He'll look like a0 plus a1x plus a2x squared plus a3x cubed plus going on forever. So I can write that out here. So this here is a0 plus a1x plus a2x squared plus a3x cubed plus a4x4 plus a5x5 plus a6x6, and I only found 6. Now I just plug in what they are. A0 was itself, A1 is itself, A2 is minus A0 over 2 factorial. A3 was minus A1 over 3 factorial, from what I recall. Yes. A4 was A0 over 4 factorial. A5 was A1 over 5 factorial. A6 was A0 over 6 factorial. And we have that. Now what you can do is you can notice you can group guys by the A0s and the A1s. So for the A0s, I would have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. Are we missing? Oh. I want to double check my signs there. I think we're off by a sign. A4 should be positive. A5 is a minus A3, so that should be positive. A6 has a minus A4, but A4 was positive. So that should actually be a minus sign. For your A1, you have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. I can tell you the next term is going to be x to the 7th over 7 factorial plus dot, dot, dot. All right, do we recognize these guys? Because that's a nice pattern. They might be something. It's sine and cosine. Not sure why you have a question mark there. Because yeah, the first one is cosine. And the second one is the sine function. This is based on the table we should have memorized up here, right? If you were to actually write this guy out, right? That would look like 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial, da da da. This guy's the odd one, so it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus da da da. So you should know what these guys look like in expanded form as well. E to the x looks like 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial plus da da da. And of course, this guy looks like geometric series 1 plus x squared plus x cubed plus x4 plus da da da. Right? So these guys that we just figured out are actually the cosine and sine, which is great because that actually coincides with what we know the answer should look like. Like if we wanted to do this without series, we would get to that answer very quickly. And the first example, I wanted to do an example where you would know what the answer would look like so you can actually see, hey, there's something to the series way of doing things. Like even when we could get a nice answer, the series is actually going to give us back that answer. So that's pretty neat. But again, let's go over the process. Basically, you have something that you want to solve by series and you center it around a certain point. You make the assumption. That's always going to be your assumption, where your x naught is going to be a specific value. Either they're going to give you x naught or they're going to list the initial conditions, and the x naught is where the input for the initial conditions. So you make that assumption, you find the derivatives, you plug it in. Now your goal is to combine all the series so that you can equate coefficients. You can, first, you have to get all the x's to have the same power. Better to have the power that you assumed in your assumption for the solution. Then you have to make sure your series start at the same point. That way, now your x to the n is a common term that you can factor out, and your series you can combine into one series. So you have two things. You have to fix the powers first, then the index. Once you do that, you can equate coefficients on both sides. Now, if this was a non-homogeneous equation, what you would do is on the right side, you find the power series for that whatever function is over there. And then you'd have, and then again, you'd set the coefficients here equal to the coefficients here. You get the recursion formula. This formula helps you find all the A's. Your A0 and your A1, they're always going to be given as if we're doing a series solution about an ordinary point. Or you just leave them as A0 and A1 and you write everyone in terms of those guys. If we were in a third order, you would leave everyone in terms of A0, A1, and A2, and then use a recursion form for everybody else. So it goes up, it bumps up by the order, right? So the first n terms are known for an nth order differential equation by assumption. So use that recursion formula, plug in successively larger n values to get what those A's are, and then you can actually write it out. Every now and then you notice a pattern. You're like, oh, I recognize that series. This is very rare though. Most of the time, what's in here is going to be gibberish to us. It's going to be what the answer to the differential equation is, but it's not going to be in a form that we can readily recognize. So what we can do instead is maybe approximate the solution. And this is where what you learned in Calc 2 about approximating series would come in handy. And you can just approximate to within a degree, any desired accuracy that you want. And yeah, that's basically the process. Very long-winded explanation, but that's how we can get through it. We'll try to go through some more examples a little bit quicker, but in the meantime, questions on anything that happened? Do we get what happened? Because you guys were very quiet this whole time. I want to make sure that we know what's going on. So are we good? Are we okay? Okay, all right. So let's do some more examples. Boom, B. So this one, going to write out maybe a little bit quicker, maybe not as quick as I could, but a little bit quicker than the last one. Actually, maybe I want to try. Yeah, let's do this. Okay, so here is what we're going to do. This one has a slight variation on it, but it shouldn't be too much trouble. So we're going to assume our y equals the series of an x minus 1 to the n. So notice here that x minus 1 is our variable. Now, it behooves you to write all your variables in terms of the variable of the power series. So we should express all other variables in terms of x minus 1. Or, here's another option just to start off, do a substitution. Because writing x minus 1 over and over, it's going to get annoying pretty fast. Make a substitution so we can write a single variable. So here's what that would look like. So I would say here something like say z equals x minus 1. This means I can write my x as z plus 1. And this means the ODE becomes y double prime minus, notice it says xy prime, but my x is now actually z plus 1. And then minus y. So, and our proposed solution is so it makes it a little bit nicer to write out. So now what I'm going to do is I'm going to plug those guys in. I would have the series n goes from 2 to infinity of n minus 1 a n z to the n minus 2. That's the second derivative. Minus z plus 1 times the series of n a n z to the n minus 1. That's the first derivative, and I can bump that index up. Minus the series of a n z to the n. So we'll have that. Oh, okay. So some people actually did work through these problems. That's why you guys are quiet. Okay, that's good to know. So yeah, now what we can do. Again, you want to combine series. So what you'll probably want to do is actually expand this. I can actually multiply the z in. That's going to bump up this power. Then I have a 1 times that, so that's n z to the n minus 1 minus now fix the powers. For my first series, I can shift all n's to n plus 2's. That will make this start at 0. That one is actually fine. Here I'm going to shift all n's to n plus 1's. And this one is fine. Notice here, I can bump this back down to 0 at will because it's not going to change anything. Can start from n equals 0 without consequence. So, because if I start from n equals 0, when I plug in n equals 0, I would just get 0 in the first term because of this guy right here. So knowing that I can start all the series from 0 and they all have a common factor of z to the n, I can now actually plug them into one big series. N plus 2, n plus 1, a n plus 2, minus n a n, minus n plus 1, a n plus 1, minus a n, all of that times z to the n equals 0. We can now equate coefficients. And at the same time, I'm going to actually do I want to do that at the same time? Maybe. Let's not get ahead of ourselves. Okay. Solve for the a n plus 2. This will be, moving this over, I would have n plus 1, a n plus 1. I would also have plus n plus 1, a n over, I would have n plus 1 times n plus 2. The n plus 1 is a common term. I can factor it from the top and cancel it. So I would have a n plus 2, a n plus 1 plus a n over n plus 2. That's our recursion formula. And so now we can actually find all the other guys. So here, our A0 is itself. Our A1 is itself. Our A2, now I start plugging into that formula, n equals 0. This will give me A1 plus A0 all over 2. A3, I can plug in n equals 1. This will give me a2 plus a1 over 3. And so that I can do a1 over 2 plus a0 over 2 plus a1 all over 3. So that's 3 over 2 divided by 3, so that's a1 over 2 plus a0 over 6. And I mean, at this point, depending on how much you're asked for, I think in the problem I asked for 4 terms or something like that. We could stop here. You'd only continue if required, but not necessarily here. But we'll stop here. And now you can actually write it out. This means your y equals a0 plus a1x plus a2x squared plus a3x cubed plus ... And so now let's actually start plugging those guys in. So we have a0 plus a1x plus our a2 is a1 over 2 plus a0 over 2. a1 plus a0 over 2 times x squared. Our a3 is a1 over 2 plus a0 over 6 x cubed plus ... This guy would look like, if I group all the a0s, 1 plus x squared over 2 plus x cubed over 6 plus ... plus a1 times x plus x squared over 2 plus x cubed over 2 plus ... That's my series solution. Now, this is not a guy we recognize, at least I don't. That pattern for that series doesn't look really familiar to me. Especially here, you have 2's under the bottom. Yeah, that's kind of weird, but yeah, that's what this answer would look like if you wrote out, well, technically it's the first 6 terms, or if you want, it's up to the x cubed term. But yeah, and again, these guys here, these functions, like this would be like your y1 from a homogeneous solution, and this would be like your y2 from the homogeneous solution, right? And the a0 and the a1 are kind of like your c1 and c2s, right? So they correspond to everything that we've been doing. It's just that you might not know a nice way to solve the ODE. And believe it or not, the techniques that I've been showing you this whole semester can't actually work on that guy. That guy is linear, but it's not constant coefficients. The solution, you cannot really assume that it's going to be exponential because of that x there. It's kind of weird to have that x there. But that is a power series solution, which we can approximate to within any degree desired accuracy we want. I keep saying degree of accuracy, but I don't want to say degree when we have another thing. C is a variation on that, this problem. So C was the same problem, except in C, I just pretend that I gave you the initial conditions. So in C, same equation, centered around the same point, except here you're given initial conditions. So if this were the problem, wait, did I? Oh, we had a Z here. So technically these x's are z's, and we should replace them with z minus 1. So technically here, these are all z's. I forget we did that change. If we wanted this in terms of x's, we'd have to replace the z's with the x minus ones. It's been a long day, so I'm half asleep over here. You guys gotta keep me honest by looking at making sure I'm actually doing the back substitutions and all that stuff that I should be doing. Now here is something. So if this were the problem, I would just repeat what I did above. A0 is the initial condition for the y, and A1 is the initial condition for the -1. And so here, what we would have is we would end up with the solution, this solution right here. Except I now plug in a 2 in the position of A0. And I would plug in a -1 in the position of A1. And that would be our particular solution. So nothing else would have changed. It also said, show that y1 and y2 for the above are linearly independent. Now here, y1 is equal to 1 plus and y2 is equal to, well, that got x minus 1. All right, so how could I show that these two are linearly independent? Let's see if we, so this is from a couple classes ago, but hopefully you remember. Like I have two answers here. How can I know that they're linearly independent? Ideas? So I found the power series solution to this equation up here. Check if what? Okay, how would you check that? We have an infinite number of terms here. There's a nicer way. Bronskin would be how I would try it. In fact, to show independence, we just have to show the Wronskian is non-zero at x naught, because then it'll be non-zero on the open interval of the solution, because we know from Abel's theorem that the Wronskian is a constant times an exponential, so if it's non-zero, it's always going to be non-zero, because the c would have to be non-zero to get a non-zero point at all. And so once we can show that at one point in the open interval where the solution lives that we have a non-zero Wronskian, these guys are going to be linearly independent, at least linearly independent on that interval. Then the y1 and y2 will be linearly independent on the open interval containing x naught. So that's what I'm going to do. And we remember that the Wronskian is just y1, y1 prime, y2, y2 prime. So that's y1, y2 prime minus y2, y1 prime. And so if I actually find the derivatives here, this guy looks like x minus 1, or so this guy here. I don't think I found any other terms. Derivative of that is 0. Derivative of this is just going to be x minus 1. Derivative of this is going to be 3x minus 1 squared, but 3 cancels into the 6 gives me a 2, so it's that. Okay, derivative of this guy is going to be 1. Then x minus 1. Plus 3x minus 1 squared over 2. So now our y of 1 at 1 okay, so let's see here. That was 2 minus 1. 2. This is 0 from here. If I plug in x equals 1, and here it's going to be 1. So this means the Wronskian of y1, y2 at 1 is going to be y1 times y2 prime minus y2 times y1 prime. This is 2, which is non-zero. So that's how we can check. All right. So we will stop there for now. Next time, I want you guys to try these two. Especially if you tried them already, I guess you already tried them. You can look ahead to solving power series by around singular points, because that's what we're going to cover next once we get through these examples. So what we're going to do is we're going to cover these examples. For this one, I believe we're in the situation where we had to apply one of the steps that we have not yet applied, where we had to evaluate some terms. So here, like step 3, we didn't have to use step 3 anywhere here, but I believe for this problem, we're going to need to use step 3 for this problem right here. So next time, we're going to start off with some more examples. Again, next class is going to be very computational. I'll tell you a few things afterwards. I'm going to introduce a new thing and tell you how to solve it, but it's going to be very computational for the most part. We'll get through these 2 examples, D and E, and I'll also do D. I'll do D in 2 different ways. So I'm going to show you a way to do series solutions that's a bit more refined. What I showed you is the way that the book goes through, and it's the very standard way of dealing with it. But there is some things that we can get away with that can make our lives a little bit easier. Because as you can probably see and tell, is that the algebra and the arithmetic can get pretty long with these guys. It's a lot of writing down. And so any little shortcut that we can get away with, we're going to want to get away with it. So try these for next time. Hopefully today's lecture was clear and you now know how to attack these if you didn't know how to attack them before. I had very long-winded explanations for the first example and a little bit for the second. But yeah, get through these. I will see you guys tomorrow. And yeah, our final is in about 2 weeks. So you can even start, if you got through these series and you don't want to look ahead, what you can start doing is start looking back from the beginning, or make sure that you're remembering what we were doing since the beginning, because the final is gonna come by quicker than you realize. Yes, we do have a second test. The second test is just before the final. The second test is the weekend before the final. The final is the one that's going to be cumulative, though. That's why I'm emphasizing it. The second test is not cumulative. It's just everything after. I'm willing to have it any day. Friday, I think, would be better. I could even do Saturday, but I don't know if everyone can do Saturday. So the next. Yes, Casserly. So just email me on Thursday at around noon, and I'll send you the link where you can meet me. So yeah, the second test is going to be, it's officially the 16th, but I'm willing to have it the 17th or the 18th. So yeah, you guys can start thinking about that as well. All right, but for now, we are going to end there. Oh, yes, I did see the regrade requests. I'm not finished with them yet. By Thursday, you should have all of them. Because I was dealing with regrade requests for my other class first. It's a larger class, so I didn't get around to everyone in 391. But so yeah, in a couple days, you'll have those. And we'll move on. Okay, so that's it for today, guys. Hopefully you understood everything that happened. It was very quick, but it wasn't theoretical, so I think a lot of people seem to be following. So we'll stop there and try those examples for next time, and I will see you guys in the next one.